Carbocation rearrangements. When we want to find the major and minor product for the electrophilic addition reaction of an asymmetrical alkene, then we cannot simply use the Markovnikov's rule to find the major and minor products. There is a possibility that the Markovnikov's product may not be the major product. Here is one such situation. Let's say that this is your alkene. Now what's going to happen if we are going to use the Markovnikov's rule? So between these two carbon, which one is going to get the hydrogen? So this is the carbon which has the most number of hydrogens, and therefore the hydrogen is going to get attached to this carbon, and the Br is going to go on to this carbon, right? So let's write on the product to see if that is one of the products that we have got here. So our major product is going to look like this. So this is the major product that you will be getting from the by applying Markovnikov's rule, but the actual major product that you get is this one where the bromine is attached to a tertiary carbon. But the one that we have got, we're using the Markovnikov's rule, is actually the minor product. Now what is happening here? There should be something happening in the mechanism for it to give this as the major product, right? Now let's look into the mechanism for this reaction and see whether there is something else that is happening in the reaction to give this as the major product. Let us begin by drawing the carbocations, different carbocations that is obtained in this reaction. If the hydrogen is going to get added to this carbon, then it's going to lead to the formation of a secondary carbocation. Let's draw the structure for it. If the hydrogen is going to get added to this carbon, then it's going to lead to the formation of a primary carbocation. So this one right here is a secondary carbocation, and this one is a primary carbocation. Right. This secondary carbocation will try to see whether it can be changed into a tertiary carbocation. In general, an unstable carbocation can get converted into a stable carbocation through either 1,2 methyl shift or 1,2 hydride shift. Now, how this is going to take place? There is an important thing that is happening in these reactions, and that is called as carbocation rearrangement. An unstable carbocation can be converted into a stable carbocation through 1,2 methyl shift and 1,2 hydride shift. Now let's see how this is going to happen. Let's take a look into this secondary carbocation. So this secondary carbocation is stable, but is not as stable as the tertiary carbocation, and it will try to see whether this can be converted into a tertiary carbocation. If there is an adjacent hydride group or a methyl group, then those two groups can shift to the neighboring position where the positive charge is present, and it can lead to another carbocation. Let's say that if we are going to shift this methyl group, what's going to happen? If we shift this methyl group, then it's going to lead to exactly the same carbocation that we started with. Right? So this is again another secondary carbocation. So by moving the methyl group, we are not going to get benefited at all. So this is again leading to exactly the same secondary carbocation. So we will not be moving this methyl group. But what's going to happen if I choose to move the hydride group? If this hydride group is going to move to the next neighboring position where the positive charge is present, then it's going to lead to the formation of a tertiary carbocation. Now the positive charge and the hydride group has shifted its position. So it is shifted from one position to the second position. If you're going to keep this as 1 and this is 2, the shift is taking place from first position to the second position, and therefore this is called as 1,2 shift. So through 1,2 hydride shift, a secondary carbocation has been converted into a tertiary carbocation. Now in the next step, this tertiary carbocation will be attacked by the nucleophile, here in this case Br minus, to give our final product. which is our major product. So this is a tertiary carbocation and this is a major product. Since this secondary carbocation is formed during this reaction, it will also be attacked by the bromide nucleophile, giving us this product, but this is a minor product here since the stability of the secondary carbocation is less compared to the stability of the tertiary carbocation. Let us do an example for 1,2-methyl shift now. So this is an unsymmetrical alkene. Let's draw the different carbocations that we will be getting for this reaction. These are the two different carbocations that we'll be getting. So this one is a primary carbocation and this one is a secondary carbocation. This secondary carbocation can be converted into a tertiary carbocation through 1,2-methyl shift. Here there is no hydrogen present, but there is a methyl group that is present which has the ability to go shift to the neighboring position. Right? So when you show the methyl shift or the hydride shift, you need to show that the electrons are the one that's moving. You cannot simply show that the methyl group is moving. You have to pull it with the electrons around it and shift it to the next place. So this methyl group is moving from its first position to the second position. You can keep this as first position, this as second position, or you can also do the other way. You can keep this as first position and second position. And these numbers has got nothing to do with the nomenclature. So when that methyl group has been shifted, then it's going to lead to the formation of a tertiary carbocation. So now you have a tertiary carbocation which will be attacked by the chloride ion. So the chloride ion will go and attack this to get a major product. So this will be a major product which is got from the tertiary carbocation. And we can also write the minor product. The minor product should come from the secondary carbocation, which would look like this. On the whole, one carbocation can be rearranged to another one provided it gives a relatively more stable carbocation than the carbocation that it initially started with. To summarize, electrophilic addition of a symmetrical alkene is going to give us only one product, whereas an asymmetrical alkene is going to give us more than one product, and it is a regioselective reaction, which means there is preferential formation of one regioisomer. And the stability of the carbocations is going to follow this order, where the tertiary is more stable compared to the secondary, primary, and methyl. And that is because of the hyperconjugation, which is basically the movement of the electrons from filled sigma orbital to empty p orbital. And then we also have talked about how one carbocation can be changed into another carbocation. A secondary carbocation can be converted into a tertiary, and a primary carbocation can be converted into a secondary carbocation through 1,2-methyl and 1,2-hydride shifts.